So what I'm going to do is actually the last statement by Nathan on what he crossed out. We might not need the restriction due to the no cloning theorem in terms of the information transfer that you talked about. My talk fits right in there. What I want to do is give you first give an extension of the talk I gave at EmQM17, and that work has been published by now and has been criticized by now, and it addresses the question of free will, non-signaling, non-locality, in ways how to talk about it and to find actually new language, to give it some terminology, because what always comes up in this, and then I applied this terminology to the non-local case and non-signaling, and then to the retrocausal case and non-signaling. And then I finish up with some comment on super indeterminism and universal uncomputability, which leads to the difference between determinism and predictability. And I hope I have some time to go there. Let me start with the two. So what's at issue? And these two issues have come up throughout the last 2 days constantly. We talk about, the moment you talk about non-locality, you talk about violation with special relativity, and the non-signaling principle. And there have been many ways to talk about that. And so I thought this was kind of, Gerd and I did some work together on this. We thought this was resolved. And we published a paper last year in Foundation of Physics. And to our surprise, we didn't have 10 or 15 or 100 downloads. It was the most downloaded paper in Foundation of Physics of the whole year in 2016. So there was some need to find out about this, because people are so confused about non-signaling from so many different angles. So when are these two assumptions when are these two assumptions incompatible, and when are they compatible? Also, in the same case, when is non-signaling compatible or incompatible with retrocausality? And the answer to these two foundational questions depends on the exact meaning of what you mean by signaling. And people like Howard Wiseman and also Tim Modlin, they've talked about that in their papers, and we just say, oh, as long as you can control the signal, you are safe. And I want to go one step further. I want to distinguish what's involved in signaling from a causal perspective, from the perspective of information transfer, and from the perspective of message communication. And which one is the important one? And the choices you make between those characterizes the interpretation you give to your quantum theory. So what is signaling in the non-signaling theorem? And this is, as I said, this is work Gerhard and I have done over the years. It's come out here last year. And I will look at the two non-signaling theorems of John Bell. We've heard Howard talk about the two Bell's theorems of 1964 and 76. I want to narrow down that discussion on just analyzing what was the non-signaling condition that Bell used in those two cases. And in 1964, Bell applies the concept of signaling in the signal theoretic sense. I'm going to explain what that means. And in 1976, Bell applies the concept of signaling in the communication theoretic sense. And in 1964, I think he didn't think much about it, and I think he made a mistake there. And I think 1976 was an attempt to correct that mistake, although he never said so. But in 1977, there is in fact a statement about correction. So the Bell 64 non-signaling theorem is the one that the operationalists use. The Bell 1976 non-signaling theorem is the one that the realists need to use if you're not an Everettian, if you're not into multiverse, if you're into non-local ontologies. So here's the famous statement almost all of you have read. In a theory in which parameters are added to quantum mechanics to determine the results of individual measurements without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. Now it comes. Moreover, the signal involved must propagate instantaneously, so that such a theory could not be Lorentz invariant. That's the familiar statement. And that statement speaks to signaling, and that's been used, and that's here in this statement, Bell simply identifies this non-local influence that he's talking about that we need with non-local signaling. Now, just as a reminder, I'm just going to show the classic experiment again. You have a spin-correlated electron pair in this case. You send it off to the different laboratories. Alice chooses a detection setting. She gets a measurement outcome. Bob independently chooses his detection setting, and he gets a measurement outcome. Let's say they have correlations. You have non-local correlations, and that's what you have. And this, in the conventional view, you just call a violation of measurement outcome. This is now in the operationalist model. And of course, there is no physical connection postulated here, no lambda, no hidden variables. So there is also no information transfer when you get this outcome from going from Alice to Bob's lab or vice versa. All you have is just correlations, local observations, and then after you compare those local observations, you have informational correlations. Now, in the Bohmian picture, you have, and this is just a tutorial briefly, we've talked about this before, in the Bohmian picture, as Bell said, there must be some influence of the measurement setting. This is called violation of parameter independence. Somehow, there is a non-local connection, a non-local ontology that guides the measurement outcome on Bob's side. And this is what is meant by when Bell says there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument. And that is known as violation of parameter independence. Yet now, this would imply, if you say that an influence always requires also the transmission of information, and that's what we've done in this paper. We just equate causal influences with information transfers. And in this case, you would end up with the concept of non-local quantum information transfer, which is a total no-no. It can't happen. It's not supposed to happen. People say it would violate special relativity. Though when we say that, the superluminal signal that's supposedly to go over there that is violating, what is that? In the picture in Bell 64 and Bell 76, and we have a three-level analysis here. On the one level, we look at causality and causal influences, ontic connections, ontic state, lambda. At another level, you can look at information and information transfer. And this can be a random bit sequence or not. And at the third level, since we also talk about the non-signaling theorem as a no communication theorem, not only as a no information transmission theorem. So you have to analyze these three levels to actually see, what is a signal? What does correspond to the signal? People rarely make those distinctions. They think, a causal influence is a signal, is a communication, is information transfer. That's just wrong. It doesn't hold. So what I'm going to do is going to take that apart and show how we can think about it in a new way. So in this case, you would say, non-signaling equals a no causal influence theorem. In this case, you would say non-signaling theorem would equal a no information transfer theorem. In this case, you would say non-signaling equals a no communication theorem. Which one is the right one? And people are using it in the literature, even within the ontological models framework, in many different ways that I see. And so I think we should have a common terminology to do this. This is what the operationalists often use. This is what the realists need to use. And that's what Bell has recognized in his later work. So Bell 64 defines non-signaling theorem as a no causal influence theorem, also as a non-information transfer theorem. And we've shown this already in 2014 in a paper called The Non-Signaling Theorem and Generalizations of Bell's Theorem. Now, Bell 76 defines the concept of signaling in a communication theoretic sense. What do we mean by that? And here's the statement. In 1976, he introduces work that recognizes for quantum theory the operational distinction between influences or causes and signals and messages. He introduces the dependence on agents, what agents can or cannot do. Bell considers here, of course, he introduces potential onto influences, the Beebles we've been talking about, and importantly, he divides them up into those variables that are controllable versus those that are uncontrollable, whereas the latter are no use for sending signals. So here, the most significant step for me in this paper was to separate out the notion of anti-causal influence from the notion of signaling. And still today, you're collapsing those two distinctions together very often in many kinds of analysis when you read the literature. Even papers in 2017 still don't recognize that distinction. So what does constitute a signal? Only if you know that, if you define that, can you then define what non-signaling means? So we call a signal theoretic signal. This would be a detector click. Just detecting a signal above noise. It's just a click of the detector. And that would be a signal in the signal theoretic sense. No communication going on, nothing. So Alice's detector clicks, that would be just a signal in the signal theoretic sense. And we call that a non-channel signal, and I'll show you why soon. And then there are signals in the communication theoretic sense, and that's what we call Shannon signal. Because you can use, it's just the causal influence, whether direct cause, common cause, or information transfer. Here, it could be any of these, but they must be under statistical control of an agent. So the way we came up with this terminology is by introducing this into Shannon's classical sender-receiver model, and to analyze those three stages in the evolution of a message. So we have a sender and a receiver system. Alice, in this case, can send a message, like SOS in this case, by a binary code, dots and dashes. They are under her control. Bob knows what these dots, he's aware of Morse code, so you can read this and know what the message was, SOS. Let me now disentangle communication from information transfer from causal influences. This is the Berlin TV tower. Charlie is in control of transmitting the radio waves. Now, this is a classical model to distinguish the semantics of the terminology. There's no quantum in here now. This is about distinguishing differences between information correlation, messages, and signals. So Charlie is in control of a Morse code feed. He needs help, so he can send an SOS to Alice and to Bob. If he can control the event transmission, and so SOS goes out to Alice with the radio, she has a receiver, and to Bob. And this would be direct cause information transfer, both. So there's a direct cause, radio waves going here, receiver, and it would be common cause information transfer for Bob and Alice. So of course, Alice and Bob, they're not communicating, but they are in a common cause relationship with Charlie. So in this case, you have perfect informational correlations that do communicate a message, SOS. And this is what we call a Shannon signal. It's very helpful to make that distinction. When you say about non-signaling theorem, what is forbidden by the non-signaling theorem? What is forbidden by it is the Shannon signaling part. The next step is not forbidden. And that confuses a lot of people, and that's why we've written that paper. Now, what if Charlie still sends out his dots and dashes, but he's not in control of what he's going to send? So a random event generator is generating that sequence. So he's sending out that sequence. You again have perfect informational correlations, just like in an EPR-type experiment. But in this case, you have perfect informational correlations, and there was no message communicated. So in this case, you have transmission of non-Shannon signals, just detector clicks, fully correlated, that are not communicating any message. So this is an introduction of terminology. When somebody says, how do you interpret the non-signaling theorem? Which type of signal are you not allowed to transmit? And so based on that, on introduction of this terminology, you can very nicely define the non-signaling theorem that Bell used in 1964, and we call that the axiomatic non-signaling theorem. And then in 1976, he changed to a different kind of non-signaling theorem, and we call that effective non-signaling, in contrast to axiomatic non-signaling. And that's the one that the realists must use. And in Bohmian theory, you must use this principle. And the difference, of course, is that axiomatic non-signaling prohibits the propagation of both Shannon signals and non-Shannon signals. whereas effective non-signaling, and Bell has realized that, only prohibits the transfer of Shannon signals, but it does allow the unlimited transmission of non-Shannon signals. So that's a terminology that's helpful to people, and we want to share that with you here. Now, now you can build out of this. Non-locality and non-axiomatic non-signaling are incompatible. In 1964, you're not allowed to have any ontic influences, no transmission of information, and that's why we have a no-influence theorem in Bell 1964. It's not a non-signaling theorem, it's actually a no-causal influence theorem. And in causal network analysis, that Matt Leifer has shown us and others, when we say, okay, we have violation of parameter independence in the Bohmian model, that was the first graph I think Matt showed us, and if you then say, oh, non-signaling is disallowed, what is really said there, no causal influences are allowed. However, and this means, here non-signaling means violation of causality. So I hear very often in orthodox interpretations, they say, oh, non-signaling simply means violation of causality. That's not what Bell meant in 1976. And this comes from the following, by the way. This is our first figure in the paper. If you have axiomatic non-signaling, then how do you know the axiomatic non-signaling assumption is true? It is true only if you assume intrinsic randomness, objective chance in the universe. How do you know that your experiments, like Emily told us, that you actually have objective chance, intrinsic randomness in the universe? Is because you need to assume in the experiments that the experimenter has free choice to make his settings, to contrast the superdeterminist view. But that depends, that model really has the fallacy of circular reasoning, because the use of non-signaling as a valid argument against determinism depends on the independent validity of these two assumptions. But these two assumptions are completely circular, and I'm going to come back to that in the end. And I call that super indeterminism when I have time. Now, the effective non-signaling theorem by Bell 76 is fully compatible with non-locality. Here, non-signaling means prohibition of communication, prohibition of message transfer, prohibition of controlling an event over there at will. That's what signaling really means in this context. So, all I want to do, how much time do I have left?
7 minutes, 7.5 minutes.
Okay. Now, in a retrocausal model, you have the same problem. If you imagine you have a causal influence coming from the future to the past, and I think, Ken, you mentioned closed time-like curve approaches. And if you think about all the paradoxes that Tolman's grandfather paradox, somebody traveling from the future into the past to kill his own grandfather, that is inconsistent with the existence of that person in the future, you have a paradox. The question then is, can you send? You're not allowed, of course, to send a message back from the future into the past to have your grandfather killed. That would create a causal paradox. But can one send back random bits of information? Can you have retro signaling from the future and the past? Would that create a causal paradox? Yes or no? That's something to think about. So I want to introduce these two types of non-signaling theorems. So here, in the first case, if a retrocausal model applies axiomatic non-signaling, the 64 Bell theorem, here non-signaling means no retrocausation. You can't have any causal influences in the axiomatic case. So the retrocausal models do need an effective non-signaling theorem, because in this case they are compatible, because all that's prohibited by effective non-signaling principle is the prohibition of retro-signaling or retro-communication from the future to the past. Finally, and I think Matt Leifer would ask this question, because in his talk was not, the problem was not non-locality as such, but the fine-tuning problem. Why can't we use superluminal signals or spooky action at a distance for signaling? The puzzle then does not become the incompatibility or incompatibility. The puzzle becomes why it cannot be used, why we cannot control it. And there's answers. It could be an emergent universe. It could just be a fact of emergence. Then in that case, emergent quantum mechanics would be a fine-tuned quantum mechanics. And we have to live with this. This was one option Matt talked about. But I suggest an explanation for this. And if in orthodox quantum theory, if you now include the agent in the universe, you have an agent-universe relationship. And in the orthodox approach, and also in the axiomatic approach of Bell 1964, the source of the unpredictability is intrinsic randomness, objective chance. And you might call this universal indeterminism. Agent and physical universe are subject to the same fundamental indeterminism. The in-principle unpredictability of physical events is a function of intrinsic randomness. However, in this case, and this is shown in this paper, indeterminism neither rejects nor affirms the reality of free will or free choice as a consequence of super indeterminism. In the other case, so where does Bohm's quantum theory, where in a deterministic universe do you get your unpredictability from? You get it from intrinsic complexity. And we've heard Tim Palmer's talk. That's where he was heading with his proposal. And in that model, you have, yes, you do have universal determinism. Agents and universe are subject to the same fundamental determinism. The in-principle unpredictability of events is a function here of the intrinsic complexity. Note that determinism need not be identified with predeterminism as a consequence of universal uncomputability. That's what I want to say. And what do I mean by that? I come full circle back to my opening presentation when I briefly talked about what is emergence. And there's a connection between intrinsic complexity and universal uncomputability. In principle, unpredictability of individual events is possible in emergence if they're based on self-referential recursive processes. You can imagine like a halting problem in computational theory or something like this. So all self-referential, self-feeding states would require an infinite amount of computational resources to actually predict the microscopic next event. You can make probabilistic predictions, but you cannot on a case-by-case. It would be like saying, I could predict where the raindrop falls 200 years from now in the hurricane over New York in a deterministic universe. And I think there might be a limit to that. That is an operational constraint. Mathematical physicists might not like that because you'd like your mathematics to be close to reality. But maybe in quantum mechanics, we are hitting a brick wall. And the brick wall is what agents can and can't do. And that might, and in Bohmian theory and in effective non-signaling theories, that constraint is part of the quantum interpretation and the argument that you require to distinguish between the success of different interpretations. So you can have determinism without predeterminism in these cases. And an example is, of course, deterministic chaos. So thank you very much.